Hello, welcome to the launch of our app CASTA, Clinical Assessment System for Tuberculosis Analysis. On the onset, I would like to thank the Machine Intelligence Research Group and also the conference members for accepting our paper to be presented at this 21st International Conference for Intelligent Systems Design. And I would also like to thank and acknowledge the funding provided by Science and Engineering Research Board DST-SERB of the Government of India to do this work and come out with something useful for the society over the past 2 years. Above all, I am very indebted to thank the doctoral members, Dr. Suba, Joyce, who is also a Nodal TB officer, and Dr. Singh, Dr. Julie, Dr. Moses, who are all some of the TB officers, clinicians, and immunologists who are in this domain, who are working in close collaboration with us across from various parts of South India, Chennai, Nagarkoil, Trivandrum, and so on. So this work was quite interesting and also challenging in aspects of data collection, and especially during this COVID season. Collecting data was quite difficult. Getting TB cases were really challenging for us. So we had to also look into other means wherein we got to get some of the skin test results of allergic disorders. So this test is not only very specific to tuberculin skin testing, but it is also common to any of the skin tests, like the intradermal skin testing approach that is used for screening allergic disorders. So having said this, let us go to the motivation why we went on to this work. Tuberculosis, commonly we call it as TB, right? So TB was a global burden and is also in developing countries even now. And this tuberculosis, there were around 10 million patients suffering from it globally during the years past 2018-19, according to reports of WHO. And at that time, India had accounted for nearly 27% of the cases, and second to India was China. You can see the statistics here. Second to India was China, Bangladesh, Indonesia with some 8%, Philippines, Pakistan, and most of the South Asian countries, and the rest of the others, Nigeria. And of course, South Africa and African countries together reported some 3% of the cases. And these 8 countries alone account for nearly 2/3 of the world's TB population, according to World Health Organization reports. So the trend is significant, as the Prime Minister Narendra Modi's vision to eradicate TB by the year of 2025 from India, and that is ahead of 5 years, that is based on the UN's Sustainable Development Goals. So the government has also been increasing funding for preventing and treatment of TB over 300% over the past few years. As per the National Strategic Plan of 2017 to 25, the government has a vision of achieving a TB-free India with strategies under the broad themes of preventing, detecting, treating, and building pillars for universal coverage and social protection. So this program, the National TB Program, and several others which you'll be seeing shortly, the TB programs provide various free of cost treatment, quality tuberculosis diagnosis, and treatment services across the country through the government health system. So one among these health system is NICSHE, Ni for End and She for TB. NICSHE is a web-enabled patient management system for TB management, which was built with collaboration with the National TB Elimination Program, NTEB, and it was built and maintained by the Central TB Board, CTD, Central TB Division, and the Ministry of Family and Healthcare, Government of India, in collaboration with NIC, National Informatics Center, and the World Health Organization's offices across India. And they also established several nodal centers across India, and one of the nodal officers, Dr. Suba, Joyce, is in our team, and we often collaborate to get to know what's happening along the medical frontiers across the country. And it's also a challenging task to get to know the information about the current updates from the medical domain, and also to get data for all these tests that has to be performed. So this is the motivation, so that we can develop some applications from the technological side, so that we can provide the clinicians a better way to decide on how to offer support for treating tuberculosis and for making better health care available in India in a cheap manner. Tuberculin skin test, also known as TST or the Mantox test, is a test that is used to detect the level of tuberculin infection, latent tuberculin infection in children and in adults. So, an individual suffering from TB is generally sensitive to this tuberculin injection. The individual is administered this by injecting a little amount of 1 or 2 ml of the tuberculin into the forearm, and it causes a small induration, a small boil kind of growth. And if the patient is sensitive, then within 48 to 72 hours, the patient will be able to see a bulge in that induration that was initially injected. And the clinician used to record the induration using ballpoint pen. They used to make markers around the boil, and then they used as vernier calipers or even an ordinary scale to see how much it has bulged or grown. Like the color changes or the redness around the induration is not considered, whereas they only see how much of the bulge has come out. So there can be some inconsistencies involved in this observation. So that is where we come into picture. So that which seems to be an induration for one clinician may not be an induration for another. One may say that 2 millimeter is growth, and another one may say this is not a growth, it is not a substantial growth, and that kind of an inconsistency and vagueness is still existing in the observations of this test. Moreover, to report for this test, after getting injected, the patient has to come back to the lab 48 hours, that is after 2 days or sometimes even after 3 days, to give a report. So most of the cases in India, the patient come for testing, and after 2-3 days, you see that there is not much growth, and they completely ignore, and they say that it is not reactive, and they make a decision by themselves. So by this, the test is getting underutilized. So in order to avoid all these things, we thought there should be some means of communication between the clinician and the patient. So this is not only our initiative for developing this CASTA app, not only tries to minimize the inconsistencies involved in the observations of this test, but it also tries to improve the clinician and patient interaction, and also tries to enhance the data handling by keeping a track of this historical data, so that the clinician and the patients might use the data in future. So from the patient's perspective, the patient can have it as a record, but from the clinician perspective, it can be used by other junior clinicians as a secondary source of reference for their future tests. So this test results can be stored in the repository, and how all this is done will be shared in the next section, by how it is managed in the database, how this data is processed, and all these things will be shared in the next section. So from the image processing part, what happens now? So this is the basic medical photography part, where we have, first of all, it is medical photography, it's not medical imaging. So medical photography is use of edge devices and mobiles for taking photographs. Of course, we have very high-end sophisticated systems for 3D cameras, images and scanning systems for doing these jobs of measuring the induration of the wheel very accurately, but they are really costly. And again, the patient has to come to the lab to avail those services. So our task is to ensure that the use of this test is not underutilized by the absenting of the patient from reporting for the test. So in order to ensure this, the patient has to take the photograph of this image, and that input images are obtained in PNG format from the medical photographs shot using mobile phones, and with the application of histogram equalization and grayscale conversion, the images are enhanced, and there is a contrast generated between the foreground and the background. Austru's thresholding method, very popular segmentation algorithm. So it iteratively determines the segmentation threshold by minimizing the intra-class variance in the respective classes. So the second approach we tried was the region growing method. First, number of seed points are defined individually on cropped revealed images on the upper sensitivity, upper intensity and the lower intensity levels. Then the individual seed points are examined for its closeness to the marker values or the seed values, and they are labeled as 0 or 1 based on the threshold defined in the difference in the intensity levels. So after which the current pixel and the seed pixels are thresholded based on the intensity level. Next, these regions are built, examined over 4 to 8 neighboring pixels or neighboring neighbors based on the intensity. So the corresponding region grows by joining those adjacent neighboring pixels to every seed point, which have a preset threshold and connectivity properties. The third method which we tried was the watershed algorithm. So in this method, image is visualized in 3 dimensions. One, of course, 2 the spatial coordinates, and the third one is the intensity of the image pixel. So it treats pixel and their corresponding values as a local elevation, like a kind of a topography, and has user-defined markers. The method floods the basins over the user-defined markers till the basins that are recognized for different markers run into watershed lines. So in most of the cases, the selection of the markers in the local minima of the image for where the basins are flooded. It involves choosing a minimum of one seed value or marker value inside each entity of the image while considering the background as a distinct entity. These 4 algorithms are available for the clinician. Apart from once an image is got from the medical photography technique, the clinician can draw or annotate around the boil for the first reading, and afterwards even for the consequent reading he can do that same annotation, and then these algorithms can be used for giving their own reading.
Just now we looked about the image processing algorithms and how they are implemented. Now let us look into the mobile aspect of it. So mobile, everyone around the world uses a mobile. Even you would have a mobile. And the mobile computation has come to another level right now, where you can play like PC level games right in your mobile phone, and also do many other sorts of communications, texting, messaging, and everything in just in your hand. So now we'll look into the image processing algorithms and how they are implemented in mobile computation. The old mobile architecture is divided into 2 parts, the front end and the back end. The front end is the UI UX that the user sees and uses, and the back end is the background applications which are running in a server somewhere, which has all the logics and all the processing that happens, which then gives you the desired result that you want. The backend architecture for our CASTA app has 3 parts. The first one being the Node.js server, and the Flask server, and the Mongodb. Coming to Node.js, many of the web developers would know about Node.js because they would be using that for their programs. There is like MERN stack, and there are many other stacks which involve Node.js. So we are using Node.js as the main server for our application, and that will act as the main endpoint for which our app sends the request to get the response. Then we have the Flask. So Flask, we use it as a microservice which does all the image processing, and it runs all the image processing code from Python and sends back the results to Node.js server. Then we have MongoDB. So MongoDB is a NoSQL database. It has a document-oriented object, and it is very useful to our use case because all the images and all the URLs act as like a document database. Coming to the front end. The front end is the UI UX which the user uses, and we use React Native to build the front end. Why we use React? So React Native has been built by Facebook itself, and it's a very big library just because it can be used to create applications for Android, for iOS, for web, for Windows, or any platform you would like to have. So for our application, the CASTA application, we want both the iOS users as well as the Android users to get benefit from it. So therefore, we are using React Native so that we can create one code base and create one whole application and deliver it for both Android users as well as the iOS users. The front end and back end communicate via HTTP REST API protocol, and we also use something called Amazon Web Services and a service called S3 in that. So what does S3 do? So S3 is a service which AWS provides, which can help us to store images, files, or anything, any data related matter. So whatever the images that we get from the user and whatever the images that we process, we send it to AWS S3, and we get the URLs from there to store in our database and to deliver it to our users to view it in their app. We have deployed both the Node.js and Flask server in an Oracle instance which runs 24/7 so that we have a good uptime and that users can use it anytime they want. We use Expo in React Native. Just that it is a library which will convert all the code that we have into build files, which can be then sent to iOS and Android app stores. So here I have the CASTA app installed in my tablet. So let us see how the CASTA app will look in your mobile devices or in your tablet devices. So once you open the CASTA app, you have the welcome screen with two options: to pick an image from the gallery, and the second option to capture an image from the camera. So if you have already taken an image and it's in your gallery, you can just click the first option and just choose it. And if you want to take a picture right now, you can select the second option, and which will open the camera app and you can take a picture out of it. So let us click the second option and take a picture. So I'm taking a picture of my hand now, and once you click it, you can press OK, and then you're given the screen to crop the image. So you can crop the image where the boil is. So I'll crop it right here, and then I'll click on crop. And now this will send the data to the server to process it. Now that the processing is done, we have the result here, and you can circle around the boils or scars that you have. Right now I don't have any boil, so I'll just circle this part which is a bulge in my hand. And once you are done with that, you can click on submit. And once you submit, you get the result of with many different algorithms. So here is the result for region growing, where you can take the slider to change the cutoff frequencies for the algorithm. So here you have different area perimeter, and you have different images for the different frequencies. Now you can switch to another one. So right now we saw region growing. Now let us switch to watershed, and you get the image processing image of the watershed algorithm. Now again you can switch the slider and see different images for the same. And if you want to see the original image, you can click here, and here you have the original image, and you can click on toggle drawings to see the image drawings that you've drawn before. And now we can click back to the original image process image, and now we can still see the other processed image. So we have all the four algorithms which are running.
There are many more extensions that we can implement in the app. The first one being camera calibration. So right now, when we take an image, the camera is not calibrated to the measurement and the height at which the image is taken. But we can make a proper calibration so that the focus and the measurements will stay same whenever you take the image. The second one being the dynamic detection of wheels. So right now, when you have to take a photo, you take the photo and you upload it to the server and then you get the result. But instead of that, we can have a model where when we come near close to a wheel, the camera app will already tell you that there is a wheel there and will highlight you the wheel around it. So we can implement these two, and there are many more extensions that we can implement into the app.
Yes, as Jonathan rightly said, there are many more extensions, a lot more to do, and we are planning to deploy this app CASTA in the Google Play Store with the initial versions, but we are planning to extend and develop it many more steps ahead. We want to even incorporate data management strategies by incorporating PDF generation, data management on the cloud, and many other services together with this. So initially we will be deploying a basic version in Play Store. So we welcome you all to download it and use it, and feel free to give back your suggestions and your feedbacks on this, so that it will enable us to improve the product even more, so that we can serve the community in a better way. Furthermore, if you have any queries regarding the image processing aspects or the algorithm aspects, you can contact me. And if you have any queries regarding the clinical aspects of the work, like how to go about the sensitivity analysis of tuberculosis or allergen skin test, or how the tests are administered, and all these kind of clinical details about this work, you have our team of doctors, Dr. Suba, Joyce, and Dr. Bhakta Singh. You can contact them. And if you have any queries regarding the technical aspects of this work, about the implementation, the server side, the database, and all these things, and the app, mobile app, of course, you can contact Jonathan, who is also available. So finally, thanks for watching. If you have any queries, we are freely available unto you. You can contact us anytime. Thank you.